Hello. Today we're going to be addressing section 1.4, property of functions. So the first thing that I want to do is talk about how we determine if we have an odd, even, or neither function. So before we do that, let's talk about some definitions. And so the first definition is for even functions. A function f is even if for every number x in its domain, the number negative x is also in the domain, and f of negative x is equal to f of x. Basically, if this checks out, we're going to end up having an even function. For an odd function, the definition tells us that a function is odd if for every number x in its domain, the number negative x is also in the domain, and f of negative x is equal to negative f of x. So basically, with the odd function, what's going to end up being the result is we're going to get a negative value for the whole function. So I'll show that in just a second, but I wanted to give that to you. One of the important things to talk about is also a theorem, and that theorem tells us that a function is even if and only if its graph is symmetric to the y-axis. That's important. It's even if it's symmetric to the y-axis, and it's odd if it's symmetric to the origin. So that's telling us that it's going to be symmetric to the origin, not the x-axis. Don't get that confused. So let me show you how we do that. And so here's our first example. What we're going to do is we're going to determine if this is an odd or even function by substituting negative x in for every x value. And so we're going to get negative x squared minus 5, and then we're going to simplify this. So negative x times negative x is going to give us a positive x squared minus 5. We notice that that is equal to f of x, and since that's equal to f of x, we see that f of negative x is equal to f of x, and that from this one here tells us that this is therefore an even function. So that's important. Let's do the next example. We're going to follow the same routine, and so we're going to get f of negative x is equal to negative x cubed, but since we have a product of three negatives, we're going to end up with negative x cubed, and that's equal to negative f of x. That shows f of negative x is equal to negative f of x. Fix that equal. And that therefore demonstrates that this is an odd function. This is an odd function. And we can see that from this definition here. That's how we demonstrate odd and even functions. Okay, to show that something is increasing, graphically, all it's doing is taking a point to another point and having some curve or a straight line. And what's happening is as we're moving to the right, moving from left to right, we see that the y values are increasing. And so in this case, we can see as we move from -1 to, I think that's 7, in the x values, we see our y's are increasing. By that same reasoning, if we have a function that is dropping in value as I go from left to right, this thing is said to be decreasing, and the way that we say decreasing or increasing on both of these, it's going to be the interval from the x value to x value. So in this case, it would be from -2 to 6. So this, we would say this function is decreasing from -2 to 6. In the increasing one, we would have gone, it's increasing from -1 to 7. Just so you guys can see the terminology and understand it. If we have a constant function, all that's telling us is that the y value is not changing. So here's x, here's y, here's our origin. If I were to have something that went straight across, this is a constant. So in this example, this is 5, so y is equal to 5. There is no change in increase or decreasing, it's being constant. Okay. For local max and min, if I do something like this, in fact, maybe I'll even increase beyond that. To get a local max and min, what's happening is it's showing this point here would be considered a local max, because as I look to the right of the point and to the right of the point, those values are lower than this point in particular. So this would be a local max. This one down here is going to be a local minimum, because as I move to the left and right, the values are bigger than this value. This is the smallest value within that region. The extreme value theorem tells us that if we have a continuous function on a closed interval, now that's important, it's got to be a closed interval from a to b, then f has an absolute maximum and an absolute minimum on that interval. So in this example that I showed you, I drew the arrows so you guys could see it's not a closed interval, it's actually continuing. And so those are local max and mins. One important thing to state, and I can draw that same picture or something similar to that so you guys can see. I want dots actually for this. This here then is going to be a local max, but because we're on a closed interval from, let's say, -5 to, that looks like 8, this local max is also an absolute max. And so if I were to ask you for local maxes, the local max for this would be 5, because we're talking about the value. If I were to ask where it was happening, you would give me the value for the x-coordinate, which is 0. If I asked for a local min, it would be this guy right here. We're going to say that's at 5, -5. That local min value would be -5. Where does it occur? It occurs at the x value 5. Now, in this case, because it's just a simple loop, our absolute maximum is going to also be 5, and our absolute min is going to be -5. They're the same. So an absolute maximum can also be a local, but not all locals are absolutes. That's something important for you guys to understand. Absolute max and mins are sometimes called extreme values because it's dealing with y, or they're called the extrema. That's something that I wanted you to know. It's the vocabulary that's so important. Now, the next thing that we're going to talk about is the average rate of change, or the average rate of change. And the average rate of change should look very similar to something you've seen in the past. It should look like slope. And in fact, the average rate of change for what we're doing here is going to be slope, and we're going from A to B. So in our example that we have, we're going from A to B. So when we look at this to find the slope of this, to find the average rate of change, it's going to be f of 3 minus f of 1 all over 3 minus 1. Well, f of 3 is going to be 3 squared times 3, which will give us 27. F of 1 is going to be 1 squared times 3, which is going to give us 3, all over 2. And so we're going to end up with 24 over 2, which gives us a average rate of change, an average rate of change of 12. So the way that this function is moving from the point 327 and 1, 3, the average rate of change there, or the slope, is 12. Let me show you in an example kind of what I mean by that. So I'll draw this for you, but it will be it's going to fall off of the graph, unfortunately, because it's such a big value. 327 would be way up here, right? Way up there. And then 2 would be at 12, somewhere around there. So this picture is going to look like this. It's a parabola. It looks like this. And the average rate of change we're looking at is from this point to this point. And so when we find the slope of that, it's almost going to look like the curve itself because it's so steep. We can see that this slope, the slope of this red line, is the average rate of change. So remember that the average rate of change is the slope of the 2 points. That's important. Okay. So we see there's a theorem. It talks precisely about what I just said, the slope of the secant line. So this line that I just drew here in red is actually the secant line. That's kind of sloppy. It's the secant line for the 2 points from 1, 3 to 327. And the average rate of change, or the slope of it, was that 12 that we got. And that's what this theorem is saying, that the average rate of change is equal to the slope. Okay. Let's do an example. And so in this example, I'm asking to find the average rate of change, and so now we know that the average rate of change is the slope. So we're going to go f of 1 minus f of negative 2 all over 1 minus a negative 2. This is the average rate of change, and I'll use triangle for change. And so f of 1, we're going to plug into the value 1 squared. In fact, I'll show it. 2 times 1 squared plus 1 minus, we're going with negative 2, f of negative 2e. My apologies, I'm plugging directly in. 2 negative 2 squared plus 1 all over 1 plus 2. That's going to give us 1 squared is going to give us 1, times 2 is 2, plus 1 is 3, minus negative 2 squared is 4, times 2 is 8, plus 1 is 9, all over 3. And we see that the average rate of change for this is a negative 2, or the slope is a negative 2. That's important because in the next thing we're going to do, the next process is finding the equation of the secant line. And to find the equation of the secant line, we need the points. Well, at negative 2, we already found that f of negative 2 was 9. And how did I know that? From right here, because this process was finding the f of negative 2. 1, the f of 1 then is this 3, because we found that, so we know that point right there. And to save us some time, because we found the average rate of change, we know that the slope is a -2. Now, the process that I would use for this, I would use the point slope form. Some people like to use the slope intercept form and then solve for b. That's fine if that's what you feel comfortable with. But we're given a point and a slope, I might as well use the point slope. So I'm going to use 1, 3, and the slope -2. So I'm going to go y minus 3 is equal to a -2 times x minus 1. And so I'm going to get y minus 3 is equal to a -2x plus 2. And then y is going to be equal to a -2x plus 5. This here is the equation of the secant line. Now, something important. If you would have given me just, pardon me. If you would have given me just, let me use a different color. If you would have given me just that also is the equation of the secant line. It's just in point slope form. Most people get picky and they want the slope intercept form. I won't care. Your homework, my lab might. So just to be safe, go ahead and continue to the slope intercept form for doing this. Now, I want to go ahead and sketch this so you guys can see. So here's the x-axis, here's the y-axis, and the function that we're given, we have these values at 1, 3, and at 2, -2, 9, which is up here, so we should have this and this. Here is our parabola. The secant line, I'll do again in red. It was from -2, 9, and 1, 3. That red line is the secant line, and the slope of that corresponding line is -2, and we know that the equation for that is -2x plus 5. All right, I hope you found this beneficial and it's helpful for the homework. As always, if you have any questions, please feel free to email me for additional help. Have a great day.